Right, so this video is to help finish up our oxidation number rules. This is for section 2 of chapter 7 for chemistry, but can be used for any class doing oxidation numbers. So your objective is to give the oxidation number for each element in the formula of a chemical compound. So your rules, right? Notice some of the rules are crossed out because I don't really need them if I'm following all the other rules, but just starting from scratch, starting from number 1, right? My first rule says that if I have any given element, right, if I have a pure element, then my oxidation number is 0. So if I just had oxygen, right, diatomic oxygen, yeah, that's two oxygens that are bonded together, but I didn't need any more or less electrons than normal to do that, so there shouldn't be any kind of charge on either of these oxygens, so my oxidation number is 0, right? Otherwise, if it's other elements, say like a metal, like iron, right? If you just see a metal all by itself, that's also 0, right? Otherwise, a lot of those non-metals like oxygen, like nitrogen, like fluorine, chlorine, bromine, iodine, all the halogens, right? They tend to be diatomic, right? So you might see more than one element technically, because again, if I had a bromine here, elemental bromine is found in this diatomic state, same reason as oxygen. It's more stable when it's bonded to another bromine to finish off that octet for each atom, but that doesn't mean that it has any kind of charge. It's still neutral. That oxidation number is 0. But all metals can exist by themselves, right? You could have pure aluminum, and if you did, that aluminum would have a 0 oxidation number. So that's my rule number 1. Rule number 2 says the oxidation number of a monatomic ion equals the charge of the ion. So my first example for that could just be salt, right? Table salt has sodium and chloride in it, and that chloride ion has a -1 charge, and that sodium ion has a +1 charge. So if I have an ionic compound, the charges of those two ions are my oxidation numbers. I could take that iron and oxygen that I talked about before, react them together to make an iron oxide compound, right? And both the iron and the oxygen, when they were existing free of one another, right, in their elemental state, have a 0 oxidation number. But when they're together, that oxygen has a -2 because it's now an oxide ion, and that iron is a +2. It's the ferrous version of iron. So it'd be a ferrous oxide, as opposed to, it could have been a ferric oxide, but that would have looked a little bit more like this, because this oxygen is a -2 still, but the iron's a +3. It takes 2 +3s to balance out 3 -2s. So again, if I have an ionic compound, the oxidation number of those ions is equal to the charge of the ion. Number 3 starts including your other kinds of compounds, right? So if I don't have an ionic compound, I can still combine nonmetals like hydrogen and oxygen to make a compound like water. And we know that oxygen is more electronegative than hydrogen, which is why we talked about how this molecule, a water molecule, is going to be polar, right? That oxygen is pulling on electrons, right? Oxygen as a ion would have a -2 charge. So we're going to give oxygen a priority in this molecule, and it's going to have that -2 oxidation state. Now understand that it doesn't really have a -2 charge, but it kind of does, because again, the whole point of this idea over here is that it'd be partially negative, and it's pulling an electron away from both of the hydrogens, which is what gives it that -2. Otherwise, the hydrogens would then have to be positive to balance that out, because this whole thing has to be neutral. So each hydrogen would have to be a +1. And this is the first one that I've dealt with like this, aside from this ionic compound up here. But essentially, I like to write work below. -2 is just translated to a -2 down here because there's only one oxygen. But with two hydrogens, I'd multiply. There's actually a +2 overall for each hydrogen. This bottom row of numbers is always going to be neutral. It's always going to cancel out to make 0. So again, if I did that to the iron oxide up here, -2 times 3 gives me -6. +3 times 2 gives me +6. That's why this balanced out. Otherwise, the hydrogen and oxygen, when they're on their own, are both zeros again. Anything in its elemental form, always 0. So those are our first 3 rules. Our next rule just throws in fluorines, number 4 there, and I crossed that out for a reason, because if I was to take fluorine and put it in any compound, it's more electronegative than any other element. So if I had this CF4, carbon tetrafluoride here, right, the fluorine is already the most electronegative, and I'm supposed to give the thing on the right priority no matter what. This oxygen got a priority for a reason. Number 3 told me to do that, right? Number 3 says the most electronegative element is going to get priority, which is oxygen in the water, but it's going to be fluorine in this molecule. So fluoride has a -1 charge, and so fluorines are always going to be a -1. But that's because they're more electronegative than any other element. So if you're following rule number 3, that also covers rule number 4. So I did cross out my rule number 4 for a reason. It's because rule 3 covers that. If I have a -1 for fluorine here, it's a -4 overall. That means my carbon has to be a +4 to make this thing neutral. So I have my oxidation numbers there. Again, rule 4 not really needed. Rule 5, though, is a little bit different. So let me insert another page here. 5 says that oxygen can be weird sometimes, and essentially we're looking at a compound like this. So if I have H2O2, again, I'm supposed to give the thing on the right priority. So I'm going to try and do this, but it's going to not work out very well, right? If I think this is an oxide, if I give the oxygen a -2, 2 times 2 is -4 here, right? So I need a +4 overall with those hydrogens to make this thing balanced. But that means each hydrogen has to be a +2. Now we should know and recognize that hydrogen only has 1 proton, literally. And it had 1 electron originally. There's no way that hydrogen can lose 2 electrons to end up with a +2 charge, because it only has 1 and it only has 1 proton. So this can't be right. Meaning that if I have a peroxide, which this turns out to be, my hydrogen can only be a +1. So that means that there's a +2 here. That means that there could be a -2 for those 2 oxygens overall, but -2 divided by 2 gives me a -1. That means that my oxide, in this case, being a peroxide, is actually going to have that oxidation number of a -1. So you just have to look out for peroxides, right? So if you see a peroxide, I'm going to use a -1 for oxygen. Usually you can tell it's a peroxide, because there will be a little 2 next to the oxygen, and a lot of times that 2 doesn't reduce with another 2, like in this case. So this is the same thing. I know this is a peroxide, so I should work it out. So each sodium's a +1, but that should make sense because sodium can only be a +1. But otherwise, you could also have a peroxide with like a group 2 element that looks like this. And again, if I tried to make it a -2, that would mean that my calcium has to be a +4, and there's no way that my calcium can be a +4. So again, this should have been a peroxide. Calcium is only ever a +2, so those 2 oxygens each have to be a -1 to make this balance out. -2 +2, right? This is definitely a peroxide. So, can I have peroxides? You also have the fluorine situation, because you can put an oxygen with 2 fluorines, excuse me. And again, fluorine is more electronegative than anything else, so it has to be -1, -2. That actually makes the oxygen a +2. So oxygen essentially has 3 different possible oxidation states. It could be a -2, a -1, or it could be a +2, but also it could be neutral. Again, if oxygen was all by itself, like originally we were talking about, in this case up here, oxygen was a 0 because it was all by itself. So any element can be a 0, but a lot of elements have many different possible oxidation numbers, oxygen just being one of them. Fluorine only ever has one oxidation number though. It's got to be -1. Hydrogens are usually a +1 unless they're with a metal. So I'll need to add another page here. So with hydrogens, again, essentially when I had, sometimes things break rules, like in this case, I'll write a CH4 or an NH3, and I'm not really supposed to write them in that order in terms of when I have binary covalent compounds. We'll talk about that later. Technically, you should always put the less electronegative thing first, but I don't write these compounds this way for a reason, right? This makes them both look like they'd be acids. So since they're not acids, the hydrogens are written second, and then you just have to understand that hydrogen's getting priority here, and will end up being a +1 because this is the normal kind of hydrogen, right? +4 for all of those. So my carbon's a -4 in this case. Again, it'd be easier to see in the other context, but I never write it that way. So nitrogen in this one could get priority if I wrote it the other direction. So you'd start with a -3, which makes sense for a nitride. And that means I have to have a +3, which means each hydrogen is +1. But again, because these are written backwards sometimes, you have to know that hydrogen is almost always a +1. The only reason hydrogen would not be a +1 is if you see it in a situation like this, right? If you see that that hydrogen is with a metal, like lithium, calcium, magnesium, whatever, right? If hydrogen's with a metal, the problem with it being a +1 is the lithium wants to be a +1. So lithium can't be a -1. That doesn't make any sense. Metals hate the electrons that they have. They don't want to gain more. So this is backwards. I have to understand that the lithium is going to get priority here. It's a -1. Excuse me, saying that backwards. The lithium is going to get priority here. It's going to be a +1. And the hydrogen is going to be a -1. It would probably help if I would have written that in the right direction. Let me fix that real quick. I'm supposed to write it like this, guys. So hopefully you don't do that by accident later, but it'll happen sometimes, right? If the hydrogen's second and it's with a metal, right, then this has to be a hydride. And this is the lithium hydride. Again, lithium can't be negative, so the hydrogen had to be negative, unlike the hydrogens up above that were positive. So hydrogen with a nonmetal, so carbon and nitrogen are nonmetals, will typically be a +1. But hydrogen with a metal is going to be a -1. So again, it could be a lithium hydride like that. It could be a calcium hydride. Then you just have 2 hydrides, because then you'd have a -2 to go with the +2 for the calcium. So hopefully that kind of makes sense. There's a difference between hydrogen, that's usually positive, and that hydride that would be a -1. Number 7 says compounds, group 1 and 2 elements in aluminum have oxidation numbers of 1, 2, 3, 8 respectively. That is not necessary, right? I don't think that rule is necessary. Again, it's just like the rules before. If this is 6, this is 7, but I don't really need 7, because even if I had aluminum oxide from earlier that we were talking about, this is an ionic compound. Those ions, monatomic ions, their oxidation number is the same as their charge. So if you knew aluminum's charge is +3, then yeah, of course that rule number 7 is true, but we already know this, right? So technically, I would think that rule number 2 covers rule number 7, so I don't think it's necessary. Rule number 8, we do need. And rule number 8 says the sum of oxidation numbers of atoms in a neutral compound is always 0. That's what I've been doing this whole time. Every time I had a compound like ferrous oxide or water or that methane or whatever it happened to be, right? When I made the oxygen a -2 and the iron +2, the goal was to make this neutral, right? The oxygen and water is a -2. The hydrogens are +1. That work I did below that was a +2, -2, that always was balanced out. It was neutral. So again, this isn't something that's really new because I've been doing it the whole time. The difference being, you need to know that that's why I'm doing it. It does have to be neutral every time. If I have a neutral compound, oxidation numbers should balance out. So that's rule number 8. But we've been doing that this whole time, so it shouldn't really be necessary. Rule number 9, finally, talks about how the sum of oxidation numbers of atoms in a polyatomic ion are equal to the net charge of that ion. So this is obviously a little bit different. So if I have an ion like, say, my nitrate ion, if I have a -1 charge for this ion overall, that means that the work that I do should equal a -1. So I follow the same rules that I always follow. Oxygen is going to be a -2 here because it gets priority. So it would be a -6 overall for the oxygen. The difference being, if I want a -1, I don't want a +6 over here. I want a +5. So I know that my nitrogen is going to be a +5, oxygen's a -2 if I'm going to get that -1 charge for a nitrate. So it's just changing the math a little bit, making sure you understand that. Otherwise, I could have other examples, say like, this one has 3 elements in it. So it makes it a little bit tougher even, right? So we're going to have to learn how to do that kind of thing too. Again, overall, I want this to be a -1 because that's the charge of dihydrogen phosphate. So again, oxygen gets priority. The next thing I should actually do is the hydrogen, because I know that hydrogen, without any metals here to deal with, is definitely going to be a +1. So again, -8 overall for the oxygen, +2 for the hydrogen. In order to make this a -1, I'm going to need a +5 here again, just like that nitrogen above. 2 + 5 is 7, -8 is -1. So I know that this phosphorus should be a +5. All right, so if I have polyatomic ions in a compound for like rule 8 again, right, just an extension of rule 8, if I had like a calcium carbonate, you know that that carbonate has a -2 charge. But again, I'm just dealing with this whole compound all at the same time. All I have to really do is think about, okay, this is neutral, it's balanced. If I give my oxygen a -2, that's a -6 overall. Calcium would be the next thing I do because I know the calcium. I always work on oxidation numbers from the outside in. Start with the elements on the right. The element the farthest to the right is the first thing you should do. Then do the element that's farthest to the left, right? And then whatever's in the middle hopefully kind of takes care of itself. Because if this is the case, -2 times 3 gives me a -6. I got a +2 for my calcium. I just have to realize that in order to make this a 0, I need a +4 for carbon. Now, if I took that apart and thought about +4 -2 for my carbonate here, I should be able to see that +4 -6, that's going to give me my charge for my ion, right? So carbonate's supposed to have a -2 charge. You know that. You've memorized that, hopefully. So that works out on its own. But again, if it's rule 9 and I had the carbonate to begin with, I'd have to know to make it -2. But in rule 8, I'm just trying to make it neutral. So it should take care of itself. Otherwise, you could have a situation where you have more than 3 elements, right? They get kind of sloppy sometimes. But if I had something like this, so this is a sodium bicarbonate, this is a baking soda example. And again, I want a 0 here because the whole thing's neutral. -2 for oxygen, it gets priority just like any other time. Sodium has to be a +1. Hydrogen is really with my polyatomic ion over here. So even though I see a metal like sodium, I'm still going to assume that my hydrogen is a +1. So if I know that, and I do that with this, carbon is just going to have to work out. It needs to be a +4 to make this whole thing neutral. So that should make sense. And again, if I took these 3 numbers and I added them up, it'd give me a -1. That's the charge of a bicarbonate. So that should work out the way it's supposed to. So anytime you have more than one element, or excuse me, more than 2 elements, you just work outside in, right? Hopefully you know the outsides. Hydrogen's something you'll also always know, so other things will take care of themselves. We don't really run into other crazy issues. But again, one last example, just to make sure we know how this works. If I had this example, acetate, right? Again, I'm trying to make this equal to a -1 right now because the charge is a -1. So I'll do the oxygen first. But here I wouldn't do the carbon first because the carbon is not something I would typically know, whereas hydrogen is something I definitely know here, right? Hydrogen has to be a +1. And if this is a +3 overall, +3 - 4 already is a -1. That means the carbon's actually going to be a 0. So it's possible for elements to have a 0 even when they're not all by themselves. More than likely, they're not going to be 0, but they can be 0 every once in a while.